Light begins as a thought. Imagine a single photon, so small it feels imaginary, nudging another photon into motion. In 1917, a scientist named Albert Einstein suggested that under the right conditions, one photon could coax another into being. Identical in color, identical in direction, matching rhythm like two dancers stepping as one. That tiny, elegant idea, stimulated emission, was a seed. It did not look dangerous. It looked like a promise. Decades passed while that promise matured in laboratories and in the minds of physicists. In the 1950s, men and women working with microwave radiation built devices called masers. Those machines proved amplification by stimulated emission could be turned into usable power. But microwaves were only the start. The challenge was to push that coherence into visible light, to sculpt a beam so precise it could be measured in hairline widths. In May of 1960, a quiet lab experiment changed history. Theodore Maiman lifted a ruby rod into a machine, struck it with a flash, and the machine sighed a light unlike any the world had seen before, narrow, bright, unscattered. The first real laser beam had been born. People often describe discovery as a line, but the laser's path was a braided river. Science feeding engineering, feeding art, feeding commerce. At first, the world did not know what to do with this new beam. A solution looking for a problem, critics said. Yet problems arrived quickly. Surgeons found they could cut with less bleeding. Ophthalmologists learned to reshape corneas with millimeter precision. Industry discovered a tool that could slice, weld, and engrave, with a delicacy no mechanical blade could match. Scientists tuned lasers to reveal atoms, to measure time more accurately than ever before, to read the secrets hidden in the spectra of stars. Why did a beam of light transform so many fields? Because it carried two gifts: focus and control. Where the sunlight and a flashlight scatter and lose themselves, a laser keeps its cohesion. Its photons march like an army in formation, allowing a single beam to concentrate energy into a tiny spot. Precision made new surgery possible. Concentrated power made cutting steel, vaporizing material, and punching holes feasible. And when you can deliver power instantaneously and exactly, new possibilities, both constructive and destructive, open. Armies and governments noticed early. The promise of a weapon that fired no bullets but a directed flux of energy was irresistible. A laser could blind a sensor, burn through an engine housing, or ignite a fuel tank without shrapnel, without noise. The Cold War poured money into higher intensities and different mediums: gas lasers, solid-state crystals, fiber lasers, chemical lasers that drew explosive power from their own reactions. Researchers chased one question with obsession: how to scale energy while keeping the beam tight, reliable, and mobile. Tests followed. Labs built systems that, in controlled conditions, could punch holes through metal plates, disable optical sensors, and in some cases alter the flight of incoming ordnance. These early successes were thrilling but humbling. The real world proved a harder stage. Atmosphere fights a laser. Heat shimmer blurs the beam. Dust scatters it. Rain steals its coherence. Powerful beams need power, lots of it, and supplying megawatts on a ship, truck, or aircraft is not a trivial engineering problem. Tracking fast, tiny targets requires sensors and control systems that can predict motion and keep the beam fixed on a point long enough to do damage. In short, the physics was elegant. Turning it into military reality demanded systems engineering on a grand scale. Even so, progress crept forward. Small unmanned aerial vehicles, drones, became the first widely publicized victims of directed energy defenses. Drones fly slowly, they carry little armor, and they can be blinded or burned by a concentrated beam. For the first time, nations demonstrated a weapon that could, in theory, be fired almost endlessly, limited not by the number of shots, but by available electricity and targeting systems. That capability shifted strategic thinking. What if air defenses could be replenished not with expensive interceptors but with steady, cheap beams? Parallel to military development, Civilian life changed as lasers slipped into everyday devices. Fiber optic cables, carrying pulses of coherent light, built the backbone of a global internet. Barcode scanners in supermarkets, laser printers, and precision manufacturing lines used lasers because they were accurate and clean. Medical lasers performed eye surgery, removed tumors with less collateral damage, and enabled therapies unimaginable a generation earlier. In labs, lasers became instruments for uncovering the quantum nature of matter. They refined atomic clocks, enabling GPS to become practical and precise. The beam that sliced steel also measured time and mapped the human genome, and yet the specter of danger stayed close. The possibility of mounting ever more powerful lasers on ships, planes, and vehicles raised new questions about escalation and control. If a beam could disable a plane's sensors or melt a missile's hull, how would rules of engagement adapt? If civilian infrastructure, communication networks, or power grids became dependent on laser-based systems, how fragile did nations become to attacks on the light itself? Each technical advance folded into a new strategic calculus. Through the latter half of the 20th century and into this century, engineers solved one set of problems only to reveal more. Improved optics reduced atmospheric distortion. Fiber lasers offered efficiency and durability. Novel beam control systems tracked targets faster and smarter. Nations fielded experimental systems on ships and vehicles, using them for counter-drone and short-range missile defense tests. Yet every victory on the test range underscored the scale of the remaining challenges when the target shifted from slow, small drones to fast, armored, or hypersonic threats. This story, of a photon nudging another photon into step, of a tiny lab experiment, of surgeons and data centers and naval officers, does not end with a single chapter. It branches, it folds back on itself. Each advancement asks a new set of moral and strategic questions. The laser, born from a thought experiment, is now woven into lives, economies, battles, and the imagination of a future where beams of focused light can heal, connect, and, if pushed, destroy. The next phase of this tale is not only about brighter beams or stronger power plants. It is about how societies choose to use a technology that can be a scalpel and a spear at the same time. Light kept unfolding into new possibilities, and with every decade the beam learned to do more. The story moves now from a single ruby rod in a Malibu lab to vast facilities and ship decks where engineers fought the same old enemies: heat, power, and the atmosphere, only now on a scale their grandparents could not imagine. The theoretical spark that Albert Einstein described in 1917, this notion that one photon could stimulate another into perfect likeness, remained the heart of the machine, and every major breakthrough traces back to that simple symmetry of light. The first laser that emitted a visible, coherent beam came in 1960, when Theodore Maiman drove a pulse of light through a synthetic ruby rod and watched the new kind of light spill out, narrow, consistent, and burning with a different logic than ordinary lamps. That single experiment proved the idea could be engineered and set off a frenzy of invention. Within years, researchers had invented gas lasers, semiconductor lasers, liquid dye lasers, solid-state lasers like ND:YAG, and later fiber lasers, each design tuned to deliver coherence, power, efficiency, or ruggedness for different jobs. Theodore Maiman's moment in May 1960 is still the hinge on which the modern laser story swings. As engineers learned to shape pulses and stack energy, a division appeared between two ambitions: make the beam useful for civil life, communications, medicine, manufacturing, and make the beam powerful enough to alter matter instantaneously. Those ambitions produced different families of lasers. Fiber lasers, arriving as a practical, reliable solution decades later, proved ideal for industry and for mobile systems because they were efficient and could be scaled by combining many fiber modules. Solid-state and chemical lasers showed the capacity to dump massive energy into a tiny spot, but often brought heavy cooling and power supply headaches. Meanwhile, physics labs pursued a different trophy: Peak power, the ability to deliver an extraordinary burst in a vanishingly short time. Facilities such as the National Ignition Facility concentrated megajoules of light onto tiny fusion targets to attempt ignition, and their achievements, pushing laser energy and precision to levels that make stars seem ordinary, redefined what most powerful can mean. The NIF has delivered multi-megajoule laser shots that produced fusion yields exceeding their input in key experiments, marking a monumental step in laser energy research. But most powerful is a phrase with two faces. In civilian science, power often means total energy delivered to a target over a pulse, the kind of work NIF does to compress and heat a tiny fuel pellet for fusion research. In directed energy defense, power more often means sustained beam power at range, kilowatts or tens of kilowatts maintained long enough to heat and disable a target. Meanwhile, ultra-short pulse systems chase peak power measured in petawatts, billions of watts, by releasing massive energy in femtoseconds. The extreme light infrastructure in Europe built petawatt-class lasers that can reach record peak powers, research centers have demonstrated, 10 petawatt capability, opening experiments into high-field physics and potential future applications that today sound like science fiction. Those systems are not weapons in the conventional sense. They are research platforms that show how extreme pulses can probe matter at unprecedented intensities. The military path split cleanly, too. Navies and armies prioritized systems that could realistically protect assets, defend a ship or base from swarms of drones, intercept rockets or mortars at short range, or blind and disable sensors without producing expensive interceptors. Early operational tests proved the concept. The U.S. Navy's laser weapon system on the USS Ponce demonstrated in 2014 that a shipboard laser could function against asymmetric threats, and even received permission for defensive use in the Persian Gulf. Lockheed Martin's Athena and other fiber laser systems showed that a modular, efficient laser could bring down multiple unmanned aerial systems in tests at White Sands and other ranges. Israel's Iron Beam concept matured into an operational program aimed at countering rockets, mortars, and drones in complement to interceptor missile systems. These systems are the pragmatic face of laser weaponization. They target small, slow, or lightly armored aerial threats where beam-dwell time and atmospheric conditions permit effective engagement. Each of these systems was invented and refined for practical reasons: to lower per-engagement cost, to provide a deep magazine limited only by electricity availability, and to counter new forms of threat, especially inexpensive drones and rocket barrages that make missile interceptors financially unsustainable at scale. Engineers wanted a tool that could be pointed, that delivered damage silently and with near-instant onset, and that required no explosive logistics chain. That intent shaped designs: scalable fiber arrays for efficiency, advanced beam directors for precision, and generators or integration with ship power plants for sustained output. Lockheed and other contractors also pushed systems into higher power brackets. Helios and other projects routinely demonstrated tens of kilowatts in factory testing, moving toward platform-ready designs that could be integrated with naval combat systems. Yet real-world physics sets hard limits. Atmosphere is a cruel medium for a tight beam. Turbulence, aerosols, rain, and heat blooming scatter and spread energy, forcing beam directors to compensate constantly. Powerful lasers demand power and cooling. Mounting a megawatt-class continuous system on a mobile vehicle or aircraft requires solving weight, heat, and fuel constraints that are still under active engineering debate. Fast targets, fighters at supersonic speed or ballistic missiles in boost or re-entry, offer only brief windows where the beam can dwell long enough to inflict structural failure. That is why current operational systems emphasize drones, small boats, mortars, and rockets in their effective envelope, while strategic-level defenses against hypersonic or ballistic threats still rely primarily on kinetic interceptors and layered sensor networks. The history of invention around lasers is thus a story of matching physics to need. Einstein supplied the fundamental law. Towns and Shallow moved from thought to microwave and optical amplifiers. My man built the first functioning device that the world could point at a problem. Later, labs scaled energy to pursue fusion and fundamental physics. Industry and defense engineers scaled lasers in a different direction, toward efficiency, ruggedness, and battlefield utility. Today, the most powerful laser may be a facility like the NIF in total energy delivered to a tiny target, or a 10 petawatt research system that overtops others in peak instantaneous power, or a fielded 60 kilowatt naval or truck-mounted laser that represents the most advanced operationally deployable weapon. Each answer depends on whether you ask about peak versus sustained power, research versus field readiness, or destructive capacity at tactical versus strategic scales. The narrative moves forward not only through machines, but through the people and choices that built them. Some inventors chased curiosity, probing how matter behaved under extreme light. Others chased utility, asking how a beam could protect ships or cities. The line between healing and harm blurred as surgeons and soldiers both learned to use the same underlying physics. Today, the laser is neither purely a tool nor purely a weapon. It is an instrument whose role is decided by human institutions. As research pushes peak powers higher and defense programs scale practical systems, the next chapters will ask difficult questions. Who controls the rules of engagement for beams that leave no shrapnel? What safeguards govern research with extreme pulses? And how will nations balance the desire for cost-efficient defenses with the risks of escalation once directed energy becomes a widespread capability? The beam that began as a single coherent thought has become a mirror. It reflects our technical genius, our strategic choices, and the ethical dilemmas that arise whenever a new power arrives. The story continues as the 1970s and 1980s brought the laser into the strategic imagination of nations. Laboratories moved from proving that light could be coherent to asking bigger questions. How much energy could a beam deliver? Could it actually intercept a moving target in the sky? Could it be made mobile enough to protect a base, a convoy, or a ship at sea? Researchers pushed both physics and engineering to the limits. Gas lasers, solid-state lasers, and chemical lasers were refined, each offering trade-offs between energy, cooling requirements, and beam quality. In some experiments, lasers could burn through metal plates in seconds. In others, they could subtly disable sensors without visible damage. By the late 1980s, governments were running parallel programs in secret. The United States invested heavily in the Strategic Defense Initiative, imagining lasers on satellites or high-altitude platforms intercepting ballistic missiles during boost phase. Europe, Japan, Israel, and Russia all ran parallel research, often focusing on smaller, more practical systems that could counter aircraft, drones, or artillery shells. The promise of a weapon that fired no bullets but could see and strike almost instantly drove immense innovation. In the 1990s and early 2000s, solid-state and fiber lasers matured. Fiber lasers, in particular, proved ideal for both industrial and defense applications. Their modular nature meant multiple fibers could be combined to create higher power arrays while maintaining precision. They were more efficient, easier to cool, and could be mounted on vehicles or ships, making them practical outside laboratory settings. During this period, real-world demonstrations began. Drones and small rockets were intercepted, lasers were mounted on test vehicles, and experiments proved that directed energy could complement or replace traditional kinetic interceptors for certain tasks. Civilian applications expanded in parallel. Fiber optic communication became the backbone of the Internet, with lasers carrying vast amounts of data across continents. Medical lasers allowed surgeons to perform procedures with unprecedented precision. Industries used lasers for cutting, engraving, and welding with micron-level accuracy. Science itself,